right? So what I have to do is I have to look at the difference, and I have to take, let's say, norm square, right? Well, I won't look at yeah. So this is did I do this correctly? It's k by, this is d by 1. I want this to be as close as possible to there is a mismatch, right? So this would be k by 1, right? Should be k by 1, and this would be d by 1, right? So there is a mismatch here. So how do you fix it? So you project, and you want that projection to be same as xi, right? How do you do that? Okay, so let's modify a little bit. So this doesn't work, right? Dimension mismatch. So what I'm going to do is I'm going to ensure that this is I want d by d, right? So I'll keep it d by d itself, so that the dimensionality mismatch won't happen. But now there is an issue, right? So for example, if you project, right? So P is a projection. Now, if you sum it over all I, and I want to minimize over all P, right? So clearly P is identity. That's the solution for this, right? If you make P equal to identity, then xi minus xi 0, right? You'll get the minima. But I want to restrict my P in such a way that, this Pxi, although it appears as if it's in B cross 1, I want to make sure that some of the values can be ignored, right? So subject to some constraint on, what do you think is the possible constraint here on P? What are the possible constraint on P? Huh? What are the possible constraint on P? Yes, any idea? What do you think is this P should be? Huh? Okay, so we can say, for example, rank of P should be less than or equal to some k, right? So fine. Anything else that you can think of? Right? In that case, well, it's not straightforward, right? So what do you do in PCA? This is an optimization problem, which, well, it's a hard problem, right? It's very, very hard problem, because we will see why, especially because of these rank constraints. Ranks are hard to deal with, right? So what do you do in PCA generally? Let's look at that first, okay? And we will see why we do that later, okay, once we start studying optimization. So what is it that you do in PCA? The first thing that you do is you construct what is known as the covariance, right? So what is the covariance? This is what you do, right? I equal to 1 to n xi transpose, right? xi transpose will give you the covariance of, I mean, just one sample estimate of the covariance. So how do you estimate? For example, I give you a coin and I ask you to find the bias of the coin. What do you do? How do you estimate? You toss the coin n times, take n samples, average them, right? If I ask you to find the variance, what do you do? What is it that you will do? Yes. How do you find the variance of a coin? Probability question, but how do you find the variance of the coin? Any idea? Yes. Variance of the coin. What do you do? First, you find the mean, and then you look at each sample, subtract the mean, square, add them up, and divide by n, right? That's what you do, right? If it has zero mean, suppose I give you n samples, it has zero mean, how do you find the variance? You square them, add them, divide by n, right? Because the mean is zero. Now, how do you find covariance? See, covariance is what? Expected value of XX transpose, right? There's an expectation here. I'm finding the average of this matrix, right? I'm going to sample X from some distribution. I'm looking at the average of XX transpose. Now I don't know the distribution of X. So what do? I have samples, n samples. I'll take each sample, Xi. I'll take Xi transpose, that gives me a matrix, right? That's an estimate of your covariance, right? One sample estimate. And I can do n such things. I add them and divide by n. Okay, this is assuming zero mean, right? Okay, so what do you do after that? What do you do after this? Okay, so the second step is you have the covariance now, right? If the mean is not zero, you can estimate the mean and subtract, and you say xi minus mu I hat times xi minus mu I hat whole transpose, right? And sum it over all I and then divide by n. Okay, so now what is the next step? So typically I should look at in which direction this S has the highest component. Okay, so how do I do that? I take S and project it onto both the directions. So basically I will do this. Okay, so V transpose S V. I want to ensure that this direction doesn't depend on the magnitude of U. I will constrain it to be unit norm. Okay. What is this saying? See, if you look at xi transpose, right? On an average, I'm seeing what does this xi points to, which is the direction which has the largest component, right? For each xi on an average. That's what I'm trying to figure out here. Is that fine? Do you agree? So, for example, in the previous case, this is the direction in which probably you have the highest component, right? The other direction is this. The third direction is you should not consider because the components are very less. Maybe I'll throw it out, right? Even if there are some component along the y direction, whatever this direction, the values are so small that I'll ignore, right? That's what I'm trying to do. So, what do you think is the solution of this? What is the solution? Guess. Of course, I haven't taught you how to solve this problem, but roughly I have mentioned, right? So what do you think? In fact, I have shown what the solution is. What kind of a matrix is S? What is the first thing that comes to your mind? S is square. Okay, fine. D cross D, right? Yeah. Second, positive.
Positive semi-definite.
Positive semi-definite. Good. Then, okay, it's a square, positive semi-definite. What else you can say? It's symmetric also, right? S is S transpose. Symmetric. So you have eigenvalue decomposition. So what does this correspond to? So the solution V star is V1, right? Which is the eigenvector corresponding to the maximum eigenvalue of S, right? So this is the eigenvector corresponding to max eigenvalue, right? This is something that we saw, right? I mean, if you project it, you better align it to the max eigenvector, right? So I got the direction V1, right? Right, so I take the data and I'm going to project every data point onto V1. So what does that give us? It gives us one-dimensional approximation of the data, right? So it's just one dimension. Do you agree? Right? I don't need to consider what is the importance of that. Well, every data point in that one dimension, I can write it as some alpha times V1. So I need not deal with D entries. I only have to deal with one number, right? Alpha, right? What is the scaling? Do you guys understand this? I mean, why this is dimensionality reduction? Although, if you looked at here, right, when I wrote k cross d, I mean, it's not really k cross d, right? So there is a dimension mismatch. But why should one project onto a plane and see? It's simply because what? I want to ensure when you look at two dimension, right, in let's say large dimension, all that I need is two vectors to describe that.